Lab 3, Physics 2211. This is Caden Smith. Part 1, Black Hole Mass. The purpose of this lab is to find the mass of a black hole via the force of gravity figures obtained in simulations. The principles applied are the universal law of gravitation and the momentum principle, and the results of the mass of the black hole are shown here. The formulas applicable here are the momentum principle as well as the universal law of gravitation shown on the right. In this lab, we assume the force of gravity is equal to the net force, as it is the only force involved between our system and surroundings. Star's change of momentum is based solely on the force it experiences due to the gravity of the black hole. Because the force is not constant, the star travels in an elliptical path, we will have to use the average net force for estimating the black hole's mass. Black hole mass can be solved using the universal law of gravitation formula showed before, solving for the capital M, as it is the source of gravity, and the forces acting parallel and perpendicular affect the star in different ways. The system here is the star, and the surroundings are the black hole. Initial conditions are the star mass, which is 2 times 10 to the 30th kilograms, time shown there, and whatever the mass of the black hole ends up being. This is the code for the first part of the lab. A bunch of technical stuff at the top. Gravitational constant and the mass of the star is shown here, as well as 86,400 for delta t, which represents 1 day, as that is how many seconds are in a day, with initial time being equal to 0. The velocity and momentum update formulas are shown at the top of the screen now. Net force is equal to the change of momentum over change of time, which is Newton's second law. And here shows how the change of momentum in each direction, perpendicular and parallel, affects that net force in that direction. And here's how we calculate the mass. We solve for the mass of the black hole using the formula, and then we add up all the total masses we calculate and divide it by the number of runs we did. And this is a simulation. The arrows represent the momentum and the force experienced by the star as a result of the black hole. And as shown, the elliptical path is here. And those are the results. The mass of the black hole turned out to be 8.4 times 10 to the 33rd kilograms. Part 2 is called Don't Crash. To find the initial velocity is the purpose of this lab that the spaceship requires to avoid crashing into both the black hole and the planet after takeoff. Principles applied are the universal law of gravitation momentum principle once again, and the results show that the ship speed in the x direction is around -6 times 10 to the 6 meters per second, y being slightly higher than that, and the minimum distance achieved being around 5.3 times 10 to the 9th meters. Formulas applicable are the same except for c. The speed of light is shown here. Ship's change of momentum is based solely on the force it experiences due to the force of gravity of the black hole and the planet. The force is not constant as the ship's distance from both the black hole and planet is changing. The forces acting parallel to the ship's motion will increase its speed as before, as well as the force acting perpendicularly will change its direction. The system is a spaceship, but this time the surroundings is both the black hole and the planet. Initial conditions are the black hole mass as calculated in part 1, planet mass, and everything else is the same. And here's the code. Mass of the black hole is shown here. It's calculated from part 1 of the lab. And here are all our constants, including the ship mass of 7 times 10th kilograms. Time max is an hour, which is represented by 60 times 60 because there's 60 minutes and 60 seconds in 1 hour. Here are the results calculated by trial and error. Our direction and force of gravity is calculated here. The calculation for the change in force on the planet as well as the change in force on the ship is done separately and then added together at the end. The velocity and position update formulas for both the planet and the ship are shown here. We go ahead and run this program. You can see the planet is the blue one and the ship is the purple. It runs for 1 hour and then the simulation stops. And the closest the ship got is around 5 times 10 to the 9th meters. The rate of change of momentum is always proportional to the net force in the same directions, perpendicular and parallel. While in the simulation I couldn't get the spaceship into orbit, the initial velocities would have to be lower for the spaceship not to shoot off outside of the black hole's orbit. In part 1, errors have to do with the elliptical path, while in part 2, the errors would have to do with the speed of light.